Welcome back to the video, and we are going to prove this example. We let n factorial, which is the product of n minus 1, n minus 2, all the way to 3 times 2 times 1. Actually, it's a product of consecutive number from 1 to 3 all the way to n. And we want to prove that n factorial is greater than 2 raised to the power of n for every positive integer n such that n is greater than or equal to 4. So we are going to use the extended principle of mathematical induction to prove this inequality. That's whole for n greater than or equal to 4. Now let's get started. The first thing that I want to do is to let P of n be this statement, n factorial greater than 2 to the n. Okay? And then we get to show that. We show that P of n is true. Is true for any integer n or positive integer n such that n greater than or equal to 4. Okay, we start with the base step. Let's write the base step. And for the base step, we need to let n to be 1, which is 4 factorial. Okay, let n to be 4, okay? Let n to be 4 because we want to show that P of n is true for any positive integer greater than or equal to 4. So we need to start with n equal 4. So we're going to have 4 factorial, which is, let's calculate, is 4 times 3 times 2 times 1, which is 12 times 2, which is 24. And 24 is greater than 16, which is 2 to the 4. So, it's true for n equal to 4. So we have the base step. Okay? So, P4 is true. Next, let's take a look at inductive step. How to do with this inductive step? When it comes to inductive step, we have to assume this. So for any positive integer k, okay, such that k greater than or equal to 4, we have to assume that P of k is true. Okay, assume that P of k is true where k is greater than or equal to 4. Then try to show that. We want to show that P of k plus 1 is true. Okay. All right. Now, what do we have? From now on, we're going to have k factorial greater than 2 to the k. Okay? And then we have to consider this. So we consider k plus 1 factorial. Okay? And k plus 1 factorial is going to be k plus 1 times k factorial. Okay? K plus 1 times factorial. If we use P of k, which is true, that is k factorial is greater than k squared. So it's going to be greater than k plus 1 times k squared. All right. What next? What can we do next? We use the fact that k is greater than or equal to 4. So now it turns out to be 4 plus 1 times k squared. Okay, so k plus 1 times k squared is greater than or equal to k plus 1 2 to the k, which is turns out to be 5 times 2 to the k. And 5 is greater than 2. Okay, so right now we have 2 times 2 to the k, and it turns out to be 2 to the k plus 1. Once we have 2 to the k plus 1, so we have proved that k plus 1 factorial is greater than, okay, now is equal to this, greater than this term, and this term greater than or equal to this term, so it's greater than 2 raised to the power of k plus 1. Okay, so hence, or therefore, p of k plus 1 is true. Okay, it is true for any integer k, okay, such that k is greater than or equal to 4. Okay, therefore we have proved Pn, which is true. Okay, so Pn is now true for any integer n such that n greater than or equal to 4. Okay, therefore we have shown that n factorial greater than 2 to the n for any positive integer n, okay, for any positive integer n such that n greater than or equal to 4. Okay, that's what we have right here. Okay, so that's it for today, and see you in the next video.